In any given 24-hour period, the planet is pure chaotic motion. Lightning strikes the Earth over 8 million times. Hundreds of thousands of babies are born, and your own heart beats roughly 100,000 times. But wrapped around all that biological and natural noise is an invisible, perfectly synchronized grid. The phone sitting in your pocket is constantly communicating with atomic clocks to maintain precise time, down to the exact millisecond. Our ancestors didn't have that digital safety net. To figure out where they were in the day, they were forced to look outward, tracking the massive, slow-moving physical realities around them: the rise of the sun, the setting of the moon, and the shifting of the stars. So how did we go from tracking the largest celestial bodies in our solar system to counting invisible subatomic particles just to know what time it is? To accurately measure something as vast as time, humans embarked on a millennia-long engineering journey to break the universe down into smaller and smaller measurable pieces. At the very beginning, humanity looked up. Prehistoric humans built massive stone monuments to physically frame and track the phases of the moon, pulling a rough calendar directly from the night sky. Eventually, that focus shifted to the sun. By tracking a localized shadow, early civilizations realized they could slice the daylight into distinct hours. We found the earliest archaeological evidence of a sundial dating back to 1500 BCE, right in the Valley of the Kings in Upper Egypt. The Egyptians scaled this concept up dramatically. They constructed massive obelisks that functioned as enormous sundials, casting shadows long enough to accurately mark the summer and winter solstices. But these giant stone structures suffered from a fatal physical flaw. They were completely blind the moment the sun set or clouds rolled in. To keep time consistently, humans needed a solution they could control. That control came from shrinking timekeeping down to earthly elements. In 6th century China, people realized they could measure the passing of an hour by burning sticks of incense, which consumed themselves at predictable, reliable rates. Tracking a single hour is entirely different from dividing a whole day mathematically. To build a standard system, the Babylonians developed a base 60 counting method, and they did it using the closest tool available, their own hands. Fingers are naturally divided into 3 bone segments. Using the thumb, Babylonians counted 12 sections on one hand. Multiply those 12 by the 5 fingers on your opposite hand to get 60. This anatomical trick gave us the 60-minute hour. With the math settled, engineers still needed a physical device to track those hours when the sun wasn't shining, leading to the invention of the water clock. Early versions measured water draining out of a bowl, but as the water level dropped, so did the pressure, slowing the flow and skewing the time. The critical breakthrough happened when an inventor from Alexandria realized that measuring the steady, continuous inflow of water provided a highly accurate, measurable rise in liquid. By turning away from the unpredictable sky and standardizing measurement through human anatomy and engineered elements, humanity took its first real step toward a perfectly mechanical clock. Water and fire were eventually replaced by metal and mechanics. The first large mechanical clocks were built by Catholic monks in the Middle Ages, who required strict, precise scheduling to coordinate their daily chores and prayers within the monastery. The massive leap forward arrived with the pendulum. It standardized the measurement of a second by tying it directly to a consistent physical motion, meaning one complete swing of the pendulum equated to exactly 1 second. Over time, that complex arrangement of pendulums, gears, and springs was miniaturized and mass-produced. Suddenly, manufacturers were putting standardized time into the pockets of the general public. Yet, the mechanical era had its own physical ceiling. Gears suffer from friction, and pendulums are altered by changes in temperature and gravity. To eliminate those errors, we had to stop looking at physical objects we could hold and zoom into the microscopic. The first microscopic solution was the quartz crystal. Unlike a metal spring, this clear mineral made of silicon and oxygen offers a highly stable internal vibration. When you run an electric current through a piece of quartz, it pulses exactly 32,768 times. By counting those exact electrical pulses, a watch can mark a single second with remarkable precision. But even quartz isn't completely immune to the outside world. The crystals still vibrate at slightly different frequencies, depending on whether the ambient room temperature is warm or cool. To completely isolate time from the environment, scientists bypassed molecules entirely and zoomed straight into the subatomic realm, inventing the atomic clock. By 1967, the definition of a second was completely rewritten. It is no longer a fraction of the Earth's daily rotation. A second is officially defined as exactly 9,192,631,770 oscillations of a cesium-133 atom. Perfect timekeeping was finally achieved the moment humans stopped measuring physical movement and started counting the invisible energy states of quantum particles. For over half a century, the rotation of our planet has had zero authority over the official definition of time. We rely heavily on that subatomic accuracy. GPS satellites orbit the Earth with atomic clocks on board, calculating the minuscule time delays of communication signals to pinpoint your exact location on the ground. Today, physicists are pushing that precision to the extreme. Using complex grids of lasers and thousand-atom clusters of the element ytterbium, modern atomic clocks are reaching previously unimaginable levels of accuracy. These laser setups are so hyper-precise, they can actually register the subtle effects of Earth's gravity on the atoms themselves, allowing scientists to literally measure how gravity warps the space-time continuum. Our long quest to track the passing hours forced us to zoom all the way down to the subatomic building blocks of reality, and in doing so, we built the exact tool we needed to finally understand the massive cosmos we started out looking at.